Greetings, everybody. Learning is a hobby here. I want to go over the exercise set for section 4.1 in Terence Tao's analysis 1 in this video for the third time. I keep getting interrupted. So this is the third time I'm attempting this video. Hopefully this one will go through. Anyway, that's not your problem. Let me bring up my solutions and we'll go through it. Okay, so here's my solutions to the exercise set. The first two questions we actually already did. I actually already did the solutions for them in the summary, so I didn't write the solution over again here. So question 4.1.1 says verify that the definition of equality on the integers is both reflexive and symmetric. And again, you could just see the video that I posted yesterday for the summary for section 4.1 because I did it there, as well as the proof that it's transitive. And then same thing for question 4.1.2, which asks that we show that the definition of negation on the integers is well defined in the sense that if a minus minus b is a prime minus minus b prime, then minus a minus minus b is equal to minus a prime minus minus b prime. In other words, equal integers have equal negations. So again, that's one that I did in the summary for section 4.1. So you could see that video if you want to see the solution to that. So I'm not going to redo it over here. All right, question 4.1.3 says show that -1 times a equals minus a for every integer a. And here's the proof. Let a be an integer. Then there are x, y in the natural numbers such that a is x minus minus y. Consider -1 times a, which is equal to 0 minus minus 1 times x minus minus y, which by definition of multiplication is 0 times x plus 1 times y minus minus 1 times x plus 0 times y. And then when you simplify, you get y minus minus x, which is equal to the negation of x minus minus y, which is the negation of a. And that's the proof. All right, question 4.1.4 says to prove the identities in proposition 416. Let me just show you that real quick because there's a lot of them. Proposition 416 says that the integers are a commutative ring with identity. So we want to show all these axioms here, or well, he calls it a proposition here, but we want to show that all these properties hold for the integers. All right, so let's go through them one at a time. He does give a hint. He says one can save some work by using some identities to prove others. For instance, once you know that x times y equals y times x, you get for free that x times 1 equals 1 times x. And once you prove that x times y plus z is equal to xy plus xz, you automatically get y plus z times x equals yx plus zx for free. All right, so we did that, but let's go through my proof here. So let x, y, z be integers, then x is equal to a minus minus b, y is c minus minus d, and z is e minus minus f for some a, b, c, d, e, f in the natural numbers. So let's show that addition is commutative first. So look at x plus y, that's equal to a minus minus b plus c minus minus d, which by definition of addition is a plus c minus minus b plus d. And by commutativity of natural numbers, that's the same thing as c plus a minus minus d plus b, which is equal to c minus minus d plus a minus minus b, again, by the definition of addition, which is equal to y plus x. Therefore, x plus y equals y plus x for any integers x and y. Right, so addition commutes. Then the next one, we show that addition is associative, and you do it in the same way by showing that just using the definition gives you what you want. So if we start with x plus y first, and then we add z to it. So we take a minus minus b plus c minus minus d, and then add e minus minus f to that. If we add inside the brackets first, we get a plus c minus minus b plus d, and then we want to add that number to e minus minus f, which is equal to, in parentheses, a plus c plus e minus minus, in parentheses, b plus d plus f. And because addition of natural numbers is associative, we can reassociate. That's the same integer as a plus, in parentheses, c plus e minus minus b plus, in parentheses, d plus f, which is equal to a minus minus b plus c plus, in parentheses, c plus e minus minus d plus f, which is equal to a minus minus b plus, in parentheses, c minus minus d plus e minus minus f. That's just by the definition of addition. And obviously that's equal to x plus, in parentheses, y plus c. So addition commutes. All right, third is to show the existence of an additive identity. We don't need to show that x plus 0 is 0 plus x because we already know that addition is commutative. So I just showed that x plus 0 equals x. So x plus 0 equals a minus minus b plus 0 minus minus 0, which by definition of addition is a plus 0 minus minus b plus 0, which is just a minus minus b because 0 plus any natural number is just that natural number. But obviously that's equal to x, so that shows that 0 is the additive identity, right? Part 4, show the existence of additive inverses. And again, we don't have to show the commutative part because we already know that addition of integers is commutative. So I just show that x plus minus x equals 0. So start with x plus minus x, that's a minus minus b plus b minus minus a. And then just using the definition of addition, that's a plus b minus minus b plus a, which is the same thing as a plus b minus minus a plus b. That's the same equivalence class as 0 minus minus 0, which is equal to the 0, the additive identity in the integers. All right, part 5, show that xy equals yx. In other words, show multiplication is commutative. So start with xy, that's equal to a minus minus b times c minus minus d. And by using the definition of multiplication of integers, that's ac plus bd minus minus bc plus ad. And if you look at y times, excuse me, y times x, that's c minus minus d times a minus minus b, which again, by the definition of multiplication is c times a plus d times b minus minus c times b plus a times d. And notice those two things are the same integer or same equivalence class in the integers. Therefore, xy equals yx. Right. Then we show that multiplication is associative. Here he actually does this proof in the summary for the section 4.1. So I just redid it here, but I didn't actually do this in my video for the summary because I wanted to have the proofs all in one place. But he does do this one in the book itself. So you just again show that x times y times z is the same integer as x times y times z, and that shows that the order that you do the multiplication and whether you do x times y first and then z, and y times z first and then times x, it doesn't matter which order that you do it in. So, but I won't go through it in detail. You could read the proof here if you want to. Like I said, he does it in the section 4.1 itself. So, all right, let's do number 7. We want to show that there's a multiplicative identity, which is the number 1. And again, I can ignore the sorry, I'm getting tongue-tied, commutative part, because we already know that multiplication is commutative. So I just show that x times 1 is equal to x. So take x times 1, that's a minus minus b times 1 minus minus 0, which by definition is a times 1 plus b times 0 minus minus a times 0 plus b times 1, which is a minus minus b, which is equal to x. All right. Property number 8 is multiplication distributes over addition. So take x times y plus z in parentheses, that's equal to a minus minus b times in parentheses c minus minus d plus e minus minus f. Do the multiplication in the parentheses first. Sorry, not the multiplication. Do the addition in the parentheses first, and then multiply, and that gives you the number, the equivalence class a times c plus e plus b times d plus f minus minus a times d plus f plus b times c plus e. And then, just distribute things, and then you can regroup things and decompose it back into a sum, which gives you a minus minus b times c minus minus d plus a minus minus b times e minus minus f, which obviously is x times y plus x times z. And that shows the distributive law. Right, and we don't have to worry about property 9. This is just another version of the distributive law where we're distributing from the right rather than from the left. But we already know that multiplication is commutative, and we already know that the distributive law holds. So that follows from part 5, and part 8. So we don't have to do any extra work for that. All right. Exercise 4.1.5 says prove proposition 4.1.8. Let me show you what that says. All right, this proposition says that the integers have no zero divisors, meaning let a and b be integers such that ab equals 0. Then either a is 0 or b is 0 or both. And he gives a hint for this. He says, while this proposition is not quite the same as lemma 2.3.3, lemma 2.3.3 says the natural numbers have no zero divisors. It is certainly legitimate to use lemma 2.3.3 in the course of proving proposition 4.1.8. So here, that's what I did. So assume x, y are integers such that x, y equals 0, but x is not 0 and y is not 0. Then I'll derive a contradiction. So then x equals n, y equals m, or x equals minus n, y equals m, or x equals minus n, y equals minus m for some non-zero natural numbers. We already saw that was true from trichotomy. And I just showed that that you get a contradiction in all the possible cases. So case 1, x equals n, y equals m. Then if you take x times y, that's n times m, and by hypothesis, that's 0. But that implies that n equals 0 or m equals 0 by proposition 2.3.3, which implies that x equals 0 or y equals 0, and that's a contradiction. All right, case 2, x is minus n and y is equal to m. That implies that xy equals negative n times m, which is negative nm, which is equal to 0 by hypothesis. That implies n times m is 0. Again, that means that n is 0 or m is 0, which means x is 0 or y is 0. That's a contradiction. Part 3, x is minus n, y is minus m. That implies xy is minus n times minus m, which is nm, which equals 0. And again, that leads to a contradiction by proposition 2.3.3. And this exhausts all possibilities for xy. Therefore, at least one of xy equals 0. Okay, 4.1.6 says prove corollary 4.1.9. That's this corollary here, the cancellation law for integers, which says that if a, b, c are integers such that a times c equals b times c, and c is non-zero, then a equals b. All right, so here's my proof of that. Let a, b, c be integers, c not 0, and ac equals bc. Then ac minus bc is equal to bc minus bc, which is 0, which implies a minus, sorry, there should be, there's a typo here. Sorry, let me fix this. It should be AC here. Oh, I'm sorry. No, this is okay because our hypothesis was that AC equals BC. So that equals 0. Sorry, that works. That implies that here you can factor out the C by the distributive law. So that implies that A minus B times C equals 0, which implies that A minus B equals 0 or C equals 0. However, C is not 0 by hypothesis. Therefore, A minus B is 0, which implies that A minus B plus B equals 0 plus B, which implies that a plus 0 equals b, or in other words, a equals b, and that proves that corollary. All right, 4.1.7 wants us to prove lemma 4.1.11. I'll show you what that lemma is. That's the order properties for the integers, and there's a bunch of them. So we'll start with part A, which is we want to show that a greater than b if and only if a minus b is a positive natural number. Right, this is if and only if, so we have to do both directions. So let's start with the forward direction. So let xy be integers such that x is greater than y. Then there's a natural number n not 0, such that x equals y plus n, which implies that x minus y equals y plus n minus y, which is equal to n, which is a positive integer. Next, let x minus y equal n for some natural number n, which is not 0. That implies x minus y plus y equals n plus y, which implies that x is y plus n, which implies x is greater than y by definition of greater than. All right, so then we'll go on to the proof of part B, which says addition preserves order. So if A is greater than B, then A plus C is greater than B plus C. All right, so let x, y, z be integers such that x is greater than y. Then x is y plus n for some non-zero natural number. Consider x plus z that equals y plus n plus z, which if we just reorder, remember natural numbers commute when you add them. So that's y plus z plus n. which is greater than y plus z, and that shows the outcome. Part C, positive multiplication preserves order. In other words, sorry, just gonna reposition here. If A is greater than B and C is positive, then AC is greater than BC. All right, so here's my proof. Let x be greater than y and z positive, then x minus y is positive, and z times x minus y is positive, which implies that zx minus zy is greater than 0, which implies that z times x is greater than zy. All right, part D, negation reverses order. In other words, we want to show if A is greater than B, then minus A is less than minus B. All right, here's the proof. Let A be greater than 0, then A minus B is greater than 0. That implies that A minus B plus the negation of that is greater than 0 plus minus the negation of A plus B. That implies that 0, right? A plus B plus its negation adds 0 by the rules for a commutative ring, right? That implies that 0 is greater than minus the negation of A minus B, which is equal to minus 1 times A minus B. We showed that earlier, equals minus 1 times A plus minus 1 times B, which is minus A plus B. That means that 0 is greater than minus A plus B, and then just subtract B from, or add the negative of B to both sides. That gives you negative B equals negative B plus 0, which is greater than minus A plus B minus B, which is minus A. So minus B is greater than minus A. Right, part E says order is transitive. So if A is greater than B and B is greater than C, then A is greater than C. Right, so let x greater than y greater than z, then x minus y is positive and y minus z is positive. Therefore, the sum is positive. And when you simplify here, you get x minus z is greater than 0, which implies that x is greater than z. Right, and then letter F, order trichotomy. Exactly one of the statements A greater than B, A less than B, or A equals B is true. All right, so this just follows from lemma 4.1.5 and parts A through E of the exercise that we just did. Okay, so that proves lemma 4.1.11. Right? Question 4.1.8, show that the principle of induction, which is axiom 2.5, does not apply directly to the integers. More precisely, give an example of a property P of n pertaining to an integer n such that P of 0 is true and that P of n implies P of the successor of n for all integers n, but that P of n is not true for all integers n. This induction is not as useful a tool for dealing with the integers as it is with natural numbers. The situation becomes even worse with the rationals and the real numbers, which we shall define shortly. So I just came up with a counterexample here. So let P of n be the proposition n plus 1 is greater than 0 for any integer z. So P, if you take P of 0, that says that 0 plus 1 is greater than 0, which is implies 1 is greater than 0, and which is true. And then assume that n plus 1 is greater than 0 for some integer z. That in z, then n plus 1 greater than 0 implies n plus 1 plus 1 is greater than n plus 1, which is greater than 0. So n plus 1 plus 1 is greater than 0. So that shows that the inductive step is satisfied, and also the base step is satisfied. However, if you take an integer like -3, for example, -3 plus 1 is -2. That's not greater than 0. So this is not that statement, even though it satisfies the method, the schema or whatever for mathematical induction. It doesn't show that it holds for all integers. All right, last question for this section, 4.1.9, show that the square of an integer is always a natural number. That is to say, prove that n squared is greater than or equal to 0 for every integer n. All right, so here's the proof. Let n be an integer, then by trichotomy, n is 0, or n is greater than 0, or n is less than 0. So I just do each of the cases separately. If n is 0, then 0 squared is 0 times 0, which is equal to 0, obviously, which is greater than or equal to 0 because it's equal to 0. Case 2, if n is greater than 0, then n squared is n times n, which is greater than n times 0, which is equal to 0. But that follows from lemma 4.1.11 part C. All right, and then the last case, if n is less than 0, then n squared is n times n, which is less than n times 0, which is 0. And that follows from 4.1 point. Whoops, sorry, I have this backwards, don't I? It should be greater than 0. By lemma 4.1.1, sorry, 4.1.11 part D. And that's it. That's the last problem in this section. So let me stop the screen share. All right, guys. So we're on to section 4.2, which I'm hoping to get posted either, well, I don't know, maybe today, maybe tomorrow, but sometime soon, because I think it's relatively short. It's only like 5 pages, and the exercise set for it is also kind of short. He's going to, in section 4.2, construct the set of rational numbers. So that's what the next video will be. I'll see you guys then. Let me know again what you think down in the comments below, and I'll see you in the next video. Until that time, keep learning, everybody.